Paper says that showers may develop later, but it looks pretty clear out right now. Why carry this thing around all day? The sky is a little dark in the west. Don't want to get my best jacket wet at the picnic. Last time that I left home with an umbrella on a sunny morning, I came home without it. Even a mathematician can't outguess the weather. Reliable forecasting is still an overwhelmingly complicated problem, despite our weather satellites and computers. But surprisingly enough, even though I can't say whether or not it will rain, mathematics can help me decide what to do about this umbrella. The key word here is decide. The secret to beating nature in this guessing game is part of what we call the mathematics of decision making. This is how a mathematician would approach the umbrella decision. First, the statement of the problem. Whether it's worthwhile to carry an umbrella depends on what the weather turns out to be. If it rains, having the umbrella is definitely worthwhile. If not, not. With me so far? Okay. Next, we're going to list the possibilities and write down what will happen in each case. The technical term for what happens is an outcome. Now, I've got some choices to make, and I'm going to call those Sol's choices. I can either take my umbrella or not take my umbrella. As far as the weather's concerned, it's either going to rain or it's not going to rain. I'll put a little sun up here. Now, let's see what happens in each case. If I take my umbrella and it rains, then I'm going to stay dry. And if I take my umbrella and it's a sunny day, then I'm going to have to lug that thing around all day, and that's a drag. If I don't take my umbrella and it rains, unfortunately, I'm going to get wet. And if I don't take my umbrella and it's a sunny day outside, that's my best possible outcome, and that's just fine with me. Well, that's clear enough. But as usually happens in mathematics, we need some numbers to move things along. Now, ordinarily, I'd use statistics to estimate the probability of each outcome occurring. But here's another way to analyze a decision mathematically. I'll take the outcomes in the order I prefer them and give each one a numerical value. These values are arbitrary. They just represent how much I consider each outcome is worth to me. My first choice is obviously to stroll around in the sun, free of all cares, including an umbrella. I'll say that's worth 3 points to me. Now, I always feel pretty good on a sunny day, but then carrying an umbrella looks silly, so this outcome is worth -1 point. Now, if I take my umbrella and it rains, then I'm going to be dry, even though I don't like the fact that it's going to rain, so let's say that's a -2. And of course, the worst case, if it rains and I don't take my umbrella, we'll give that a -5. Now, the way to my decision is paved. All I have to figure out is my expected payoff. It's essentially just like gambling. If I know the odds, I can calculate how well I'll do on average.
Clouds coming up today, although I do think we'll see some intervals of sunshine.
Let's say that I listen to a weather report, and the forecaster announces there's a 50-50 chance of rain. Big help, right? This is the classic case. Even odds on the chance of rain and total indecision about taking my umbrella. But now that I've ranked my preferences and assigned values to the outcomes, I can calculate the potential payoffs. If I take the umbrella, there's a 50% chance of rain with a value of -2, and there's a 50% chance that it won't rain with a value of -1, which gives me an expected payoff of -1.5. If I don't take my umbrella, then there's still a 50% chance of rain, now with a value of -5, and there's a 50% chance that it won't rain with a value of 3, and I get an expected payoff of -1. Now, -1 is better than -1.5. Not by much, maybe, but enough. So given my set of values, it doesn't pay to take the umbrella. That's a relief. turning my preferences into numbers enables me to make a decision based on expected payoffs. That's the heart of the mathematical approach to decision-making, pinning down the preference information so that I can find the answer that best serves my interests. Of course, if you were playing this game, you could put different values on the outcomes. Then you might come up with an entirely different decision and take your umbrella. Now, most important decisions involve another factor, what other people in the world are planning. Nature doesn't make choices, and whether or not it rains doesn't depend on what I decide about my umbrella. But the mathematics of decision-making really gets interesting when you go head-to-head with someone else. A general, for example, has to decide to attack or retreat. What's the enemy planning to do? This chess player ponders whether to risk his queen. Will his opponent take the bait? Because these choices depend on someone else's choice, now we have a real contest. What mathematicians call, for obvious reasons, a game. And the techniques that have been devised for analyzing this kind of decision make up game theory, one of the important developments of 20th century mathematics. Some of the concepts of game theory come directly from traditional games like chess. Two opponents, called players, each of whom wants the maximum payoff. Now, in a strictly competitive board game, the maximum payoff is victory. One player wins, and the other player loses. Since the winner's gain comes at the loser's expense, we call games like chess zero-sum games. But mathematics enables us to extend game theory to more complex situations. Robert Axelrod, political scientist at the University of Michigan.
Most of the games that we're used to, like basketball or chess, have a winner and a loser, or they both draw, but they both can't do well. On the other hand, most real-world situations are non-zero-sum. We can both do better by cooperating, or we could both do better by avoiding an explosive confrontation or a long labor management strike. And so it's not just the case that whatever one side gets, the other one loses, as in a zero-sum game.
When you decide what kind of car to buy, you're steering into one of Professor Axelrod's non-zero-sum games, foreign trade policy. Some people advocate unrestrained free trade among all nations. Others believe we should promote our domestic automotive industry through import restrictions, duties, and other protective measures. The government generally tries to find a middle ground through mutual trade agreements with other countries. Now, trade policy is a complex issue, but the mathematics of game theory can help us to understand why this kind of agreement is difficult to maintain. We'll explore this game with the help of a whimsical example.
Welcome to Rosanadania, where life is cake.
Rosanadania is a very small country, but the citizens are justifiably proud of the cakes and cookies they produce. There is nothing more quintessentially Rosanadanian than this Rosie's pastry shop where work and pleasure go hand in hand. But since people often like some ice cream with their cake, Rosie's imports ice cream from a nearby nation, Slovenia. However, Rosanadania is also trying to build a domestic ice cream industry, which some people favor because they think it will create more employment and greater prosperity.
Greetings from Slovenia, ice cream capital of the world.
The citizens of Slovenia think their domestic ice cream is the perfect dessert. Here we've been given a rare glimpse inside an actual Steve's ice creamery. Centuries of applied research have turned the culinary art into an exact science. However, Slovenians have a particular predilection toward the excellent cookies imported from Rosanadania. Slovenia makes cookies domestically also, and would like, if possible, to promote the local product. Now, over the years, Rosanadania and Slovenia have made several trade treaties to govern imports and exports between the two countries. But such agreements are often short-lived because one or both countries come up with clever ways to circumvent the treaty. If Rosie's wants to sell more ice cream, for example, it might put a special tax on ice cream imported from Steve's. And in the same way, Steve's might offer an ice cream and cookies special, which only applies to cookies manufactured by Steve's. If the agreement breaks down altogether, an unrestrained trade war may break out and both countries will suffer. Game theory can help us clarify the problem here. We use the same format we used before, but nature is not a factor this time. There are two players who have decisions to make in this game. Each country has two strategies it can follow. It can abide by the treaty, or it can renege. In game theory terms, we call these strategies cooperation and defection. This time, instead of actual values, we'll rank the outcomes for each player, using 1 as the worst and 4 as the best. Say you're Rosanna-Dania. Your worst outcome is to continue to observe the treaty while Slovenia defects. This is called the sucker's payoff, and we give it a 1. Your next worst case is if both countries defect and your cakes can't be marketed to Steve's customers. This outcome therefore gets a payoff of 2. You'd prefer for both countries to abide by the agreement, so we consider mutual cooperation a payoff of 3. And your best payoff, 4, comes about when Slovenia cooperates while you defect. In other words, when you create import barriers while they continue to allow free trade. Now, Slovenia prefers the outcomes in the same order, so we put a second number in each cell to indicate their payoffs. Now we can see the problem. Look at the situation from your Rosanna-Danian vantage point. If Slovenia cooperates, then your best strategy is to defect, which yields a payoff of 4 instead of 3. If they defect, your best strategy is to defect, which yields a payoff of 2 instead of 1. No matter what they do then, your best strategy is to defect from the agreement. And the same analysis applies to Slovenia's strategies. From the individual player's point of view, defecting always brings a higher return than cooperating. But if both countries defect, both receive payoffs of 2, while if they both cooperate, both receive 3. Defecting therefore appears to be the best individual strategy, but if both players defect, both do worse than they would have if they both cooperated. This puzzle is what game theorists call the prisoner's dilemma. It shows up in many situations, whenever two players are caught between the benefits of cooperating and the temptation of defecting. And there's another familiar game that's similar, but involves many players. It's the game of, this is fine for me, but what if everybody did it? You know, I'm a pretty serious fisherman, and whenever I'm not too busy working on mathematics, I head for the nearest place to cast my line. Well, this is a pretty good spot that I found, and I can usually catch my limit here by mid-afternoon. Now, my individual preference would be to stay here all day and to keep all of the fish that I can catch. But what if everybody did that? Before long, the fish population will be hopelessly depleted, and no one will be able to enjoy fishing here. My personal preference for an unlimited catch is disastrous if everyone adopts it. This version of the prisoner's dilemma is called the tragedy of the commons, because it represents what happens to a common resource, such as fish in the pond, if everyone pursues the goal of maximizing individual gain. The most common response to a tragedy of the commons dilemma is regulation, usually by some organization that represents all of the players. For an individual manufacturing company, the cheapest way to get rid of industrial waste might be to pour it into a nearby river, dump it in someone's back lot, or send it up in smoke. But if all factories do this, the environmental impact is catastrophic. It's a tough decision for an individual firm to control pollution because that costs money and might lead to a competitive disadvantage. So in the case of pollution, we rely on public officials, such as the Environmental Protection Agency, to prevent a tragedy of the commons. Sometimes issues of cooperating and defecting are so bound up with ethics that effective regulation is very difficult to enact.
Yeah, Dr. Cohen's a man, and he's going to check out your heart and your stomach today, okay?
As a society, for example, we're traditionally reluctant to tell parents how to care for their children. For many years, pediatricians have recommended vaccinating infants to protect them from diseases like whooping cough. Dr. Anita Fine.
Whooping cough is quite serious. The death rate is 1 in 300 in children less than a year. Here at the plan, we've seen one child with it last year. It is a very long illness, and in fact is called a disease of 100 days, and often the children are very sick for a very long time.
Thanks for coming.
Oh, sure.
Babies usually receive 4 DPT shots. The P is for pertussis, the medical name for whooping cough, between age 3 months and 18 months.
And I want to tell you a little bit about it before we give it so that you'll know what to expect.
The vaccine, however, is not 100% safe. Every year, several dozen vaccinated infants suffer seizures, brain damage, and sometimes death. Parents are becoming understandably concerned about this risk.
If I'm dealing with a parent who's had many children, and this is another one, and they feel very confident about the low risk of problems with the immunization, then I tend to have few questions. But recently, with the amount of information being spread about the side effects of the DPT shot, we often ask questions. And we have a handout explaining the side effects. I never give it the immunization unless the parent really feels that it's the right thing to do for their child.
So what should a parent do? Partly as a result of the vaccination policy, whooping cough has almost disappeared in the United States. The individual family may therefore be tempted to refuse the risk of vaccination. But if every parent adopted this strategy, the enormous gains made in eliminating the disease would be wiped out.
Oh, done, little guy. You're going to be all right.
Whether your concern is economics or medical ethics, the mathematics of game theory is important to understanding the prisoner's dilemma and the tragedy of the commons. The challenge presented by these games is that our traditional notions of winning and losing don't work. Both players do better if they cooperate, but it's difficult to resist the temptation to defect to try for a higher individual payoff. But what about situations where an entire group wants to combine their individual preferences into a single decision they can all accept? Here we move from the realm of game theory to the more familiar subject of voting. And we all know the simplest rule for voting between two choices. The choice with the majority of votes wins. Everyone on this picnic certainly knows about majority rule. When they voted between chicken and hot dogs, chicken got a majority, more than half the votes, and people considered the result decisive and fair. But very often decisions involve more than two choices, and the vote doesn't produce a majority. Even for a group of friends, choosing among more than two alternatives can lead to problems.
Wait a minute! Whoa, wait a minute! Wait. We've got to take a vote. Come on now, this is getting out of hand. Vote. We better vote. Come on, now let's take a vote. Okay, how many people want to play Frisbee?
Yeah.
Okay, that's 6 Frisbees. How about softball? Yay! 5 softball. Okay, basketball.
Oops.
Oh, shoot. That's not going to work.
Frisbee it is.
Yeah, wait. Now, we got to be fair. There isn't any majority here.
There's 6 of us for Frisbee.
Yeah, but we got 5 and 2 is 7.
Yeah, so
Yeah, but there are 5 for softball and 2 for basketball. That makes 7.
So let's play baseball.
No sport has a majority, so the group decision isn't clear. Here's how a mathematician might try to find out what's going on.
Look. I got a way to do this. Look, Harry, who wants baseball as their first choice? Baseball. Okay, come on. Baseballs? All the baseballs over here, okay? Okay, come on. All the basketballs are first choice over here. Basketballs, stand right over here, okay? Okay, how about the Frisbees? How many Frisbees? Let's get all the Frisbees here. Now, wait a minute.
Well, it looked as if we had 3 factions here. Baseball buffs, basketball jocks, and Frisbee fans. But as a mathematician, I know that it's important to find out not just everyone's first choice, but the way they rank all 3 alternatives. And by asking around, I discovered that these 13 people actually fall into 4 groups. 5 voters prefer baseball first, then basketball, and then Frisbee. 2 voters rank the sports this way. And of the 6 people who prefer Frisbee most, 4 rank them in the order Frisbee, baseball, then basketball, while 2 prefer Frisbee first, then basketball, and then baseball. Now I'm going to propose a different kind of voting system, one that makes use of these preference lists.
Okay, guys, okay, wait a minute. Listen up, listen up. I got a method that's going to work. This simple majority rule stuff isn't getting us anywhere. Look, what we're going to do is we're going to take your preferences and we're going to throw out the game that everybody liked the least, okay? Yeah, it'll work, you know? It'll be more, yeah, in this case, that's Frisbee.
Wait a minute, wait. There were 6 of us.
The voting method I'm using eliminates the alternative which is ranked lowest by the largest number of voters. That way, fewer people will feel that they've been stuck with their last choice. In this case, Frisbee has the most last place votes.
So we eliminate it, okay? We recount, that's all right. We recount the votes, and baseball's the winner.
Yeah!
Come on, let's go. Oh, so we have to play baseball now?
Okay, come on, hit it.
Looks like a spirited game, but some people may not have accepted the group decision.
So your second place choice is basketball, right?
Right.
All right, so all we have to do is switch it. So we take basketball and baseball, and all we do is switch our preferences right around.
So I say that baseball's my second choice, even though it's really basketball.
Exactly. And I think what we can do then is turn the whole thing around. We might even get another.
Now, suppose that these two are really determined to make the group play Frisbee. They're willing, insincerely, to switch their second and third preferences. Then the preference list will look like this. When the last two voters reverse their second and third preferences, their lineup exactly matches the other Frisbee fans. Now, basketball has the most last place votes. We eliminate it, giving 2 more first place votes to Frisbee, which is now elected the winner.
Frisbee wins!
By making a minor change in their preferences, one that didn't even involve Frisbee, 2 people have brought about a dramatic change in the group decision. So our voting method has a flaw. For centuries, mathematicians have searched for a perfect, flawless voting system.
Bonk!
Finally, in 1952, social choice theorist Kenneth Arrow proved that an absolutely fair and decisive voting system is impossible. If you define fairness in terms of a few simple criteria we'd all agree to, Arrow's impossibility theorem follows as an indisputable result. That doesn't mean, of course, that people will abandon voting as a way of reaching group decisions. In fact, Arrow's impossibility theorem has sparked a revival of interest in the field of social choice. But it does mean that no voting system is completely immune to logical flaws or insincere voting behavior. There are cases, however, when a group can agree in advance to a common definition of fairness. Such an agreement makes it possible to reach a decision that will best serve the interests of all participants. Mathematicians call this technique fair division.
Hey guys, I got a split now.
Oh,
so, since I just bought this for the day, why don't you guys take it?
Thanks a lot. Thanks a lot.
Okay, I'll see you later.
Bye. See you later.
Huh. That's awfully nice.
Yeah.
Would you mind if I took it?
What? Well, you could. Actually, I was going to ask if I could take it since I'm going away next week. It'd be great to have with me.
Yeah.
Why don't we cut it in half? That would be one
That'd be
solution.
great. It'd be great. It would fly well.
I would really.
I know what we should do. We should do like a bidding situation.
Who gets to take home the Frisbee? And what does the other person get for her share? Well, a fair division method for this case is very simple. Sheila and Alice each write down how much they think the Frisbee is worth.
Okay, I'll write mine.
Boy, I don't know how much Frisbee is worth. It's worth a lot.
And like an auction, the person who writes down the higher price gets to keep the Frisbee. Since Sheila thinks the Frisbee is worth $1.50, she considers her equity, the value of her half, to be 75 cents. And Alice thinks her equity is 50 cents. Sheila's valuation is higher, so she gets to keep the Frisbee. She pays Alice the amount Alice considered her equity to be worth, 50 cents, plus half the difference between the estimates, or 12.5 cents, for a total of 62.5 cents. Since they're friends, we won't worry about the half cent. What's the result of this approach? Sheila's equity plus the 62 cents she pays Alice equals $1.37. So Sheila gets the Frisbee for less than she thought it was worth. And Alice gets more in cash than she thought her equity was worth. Both do better than they might have if they hadn't agreed in advance on a fair division procedure.
Too bad there was nothing left when we got here.
You got here late.
Let's go out to dinner then.
Yeah, that's a good idea.
Yeah, there's a
What kind of
Chinese
food?
place. Yeah, there is a Chinese place around.
We should get a whole bunch of dishes that we could just share.
Yeah, like the appetizers. You ever go out, you do that, you just do appetizers. Okay, all right, wait a minute. Peking ravioli. Right.
You bet.
Yeah.
And the sparrows.
Okay, and the sparrows.
Uh-huh.
And the sparrows.
And wonton soup.
Decision-making is a basic human activity, one that permeates both our individual lives and our social existence. We wouldn't expect to wrestle down something that profound into a cut-and-dried set of rules. That's why decision-making always has been, and probably always will be, an art. But as we've seen, mathematics can identify different kinds of decision-making situations: games, social choice, and fair division. And mathematics does more than that. In the case of games, it tells us when solutions are possible and what shape they should take. For fair division, mathematicians have devised all sorts of ingenious procedures. And for voting, the foundation of social choice in a democracy, mathematics has shown that fairness and decisiveness are ultimately impossible goals. Well, I should get going. Just think about all the decisions that those guys are going to have to make in that Chinese restaurant. I mean, splitting up the egg rolls alone is a pretty complicated fair division problem. I'm not even sure that those guys know the difference between dim sum and zero sum.